van materials. The optimization of synthesis and crystal growth by chemical vapor transport technique, the analyzing of structural and compositional characterization, and the understanding of magnetic properties using discrete magnetometry. Why I can say that this work is important now? It's because layer 2-dimensional van der Waals material, it's the very interesting kind of material. They have a stable monolayer and they can apply some special unique properties. But why our kind of material, I mean MPX3 material, interesting is because they can appear the unique magnetic properties because of their crystal structure. So about the crystal structure. This material was interesting since graphene was discovered. It is known that graphene have the stable monolayer, and here presented the crystal structure of MPX3 materials. It looks like the honeycomb, and in each corner of lattice you can see the magnetic ions. They layer between each other connected by weak van der Waals process. In MPX3 materials, in the on place of M, it's transition metal. You can put any elements from vanadium to zinc. On the place of X, you can put sulfur or selenium. To understand the magnetic structure, to describe it, you can use you can't use the only one model. So you should use model A, B, and C. In model A, the magnetic ions coupled to each other ferromagnetically, and between layers they also coupled ferromagnetically. In the model B, every magnetic ions coupled antiferromagnetically to each other, and between layers they coupled ferromagnetically. In the model C, the magnetic ions coupled as in the model A, but between layers they coupled antiferromagnetically. To obtain the samples in this work were used solid state synthesis reaction and chemical vapor transport technique. In solid state synthesis reaction, we took some components, we grain it, press it in the pellets in the samples with a smooth surface. Then we put it in the ampule, vacuum it, seal the ampule, and this prepared ampule we put it to the furnace. Then we have the high temperature, and because of this high temperature, our components started to interact to each other, and in the end we got the good homogeneously sample. In the case of chemical vapor transport, we took the powder and the transport agent. We didn't press it as in the solid state synthesis reaction. We put the powder into the ampule, and as in the case of solid state reaction, we vacuum it, seal it, and put it in the furnace. But here we put it in the two-zone furnace, and we had the temperature gradient. Because we have this furnace with the two temperatures, our material from the hotter side transferred to the colder side, and in the colder side we got the single crystals. Each sample was characterized using powder X-ray diffraction, energy-dispersive spectroscopy, and discrete magnetometry. Here you can see the samples that we obtained after solid state synthesis reaction. It was iron, nickel, phosphor, sulfur 3 samples with different amount of iron. Here it was 2.5, 5, and 7.5%. Here we got some pellets with not smooth surfaces. Before you can see tiny crystals on the surface. And for the samples, we used the temperature profile, what's shown here. Here you can see the samples. What we got after solid state synthesis, it was nickel, phosphor, selenium free. And here, for this sample, we used the same temperature profile as for iron, nickel, phosphor, sulfur free. The highest temperature was 600 degrees, but as you can see, it was not successfully. So our sample here separated into two phases, and we got the sample with a big amount of nickel here, and here we got the sample with a big amount of phosphor and selenium. So we decided to improve temperature profile and to lower the highest temperature to until 500 degrees. And here you can see the sample or what was obtained using this temperature profile, improved temperature profile, and after powder X-ray diffraction, we understood that it was better. Here shown the sample of cobalt phosphor sulfur free, and here we used the same improved temperature profile as for the nickel phosphor selenium free. I mean, with this highest temperature. And as you can see, this sample was not so successful, I mean, in this experiment, because we have like a lot of tiny crystals and some red line and the yellow deposition. So we should think how to improve temperature profile and how to improve the process of synthesis here. Okay, here shown the photo of sample of iron, nickel, phosphor, sulfur 3 cyclocrystals after chemical vapor transport technique. And you can see from the photo that our crystals have a layered structure. Yeah, you can see. And for obtaining these samples, we used this temperature profile for different side of the thermals. It was the hotter side and the hotter side. Okay. Here you can see the results after powder X-ray diffraction for samples of iron, nickel, phosphor, sulfur 3 with different amount of iron, and for the sample for the pure nickel. And the gray line is the result what we took from the ICSD crystal database for comparison results. Here shown the zoomed result for the main peak of intensity, because we want to figure out what happens if we add the iron with this peak. And as you can see, when we add the iron more and more, our peak of intensity shifts to the left side. Here are presented the results after powder X-ray diffraction for samples with cobalt and with nickel phosphor selenium free. And as I told before, our samples was not so successfully. So here you can see that not every peak, main peak of intensity was identified. So it means that we got not the only one phase sample, but the sample with the secondary or maybe third phase. And here shown the results for nickel phosphor selenium free. It was more successful than with cobalt, and because here every peak of intensity was identified. Here shown the picture which was made using scanning electron microscopy during EDX measurement. It was the powder sample of iron, nickel, phosphor, sulfur 3 with different amount of iron. And here presented the results after energy-dispersive X-ray spectroscopy. Here shown the results what was calculated, what we expected to get in our samples, and here shown the results what we got in real. So if you compare these two tables, you can see that we got the good sample with almost expected composition of components. So I can say that it was successful. And here are shown the results after energy-dispersive spectroscopy for single crystals, with 2.5% of iron and 5% of iron. And if you compare these results to that table, you can see that our amount always almost the same. Okay, after split magnetometry, we got these results. We have the 5 curves for 5 samples with a different amount of iron. Here was the pure nickel, here 2.5%, 5%, 7.5%, and 10% of iron. And you can see that our magnetic moment increases with increasing amount of added iron, and it shifts to the left side. In conclusion, I want to say that using solid-state synthesis were obtained the following samples. It was samples iron, nickel, phosphor, sulfur 3 with different amount of iron, nickel, phosphor, sulfur 3, cobalt, phosphor, sulfur 3, and nickel, phosphor, selenium 3. Using a CVD technique were obtained next sample. It was the sample of iron, nickel, phosphor, sulfur 3, and iron, nickel, phosphor, sulfur 3 with 5 and 5% of iron. For characterization, were used powder X-ray diffraction and energy-dispersive X-ray spectroscopy. And to characterize the magnetic properties was used the split magnetometry for a sample with different amount of iron and for pure nickel. And from these results, we understood that our magnetic moment increases with increasing amount of added iron. In the end, I want to say thank you so much for UKRATOP project that gives me this opportunity to have this experience of working here, and for all. Yeah, also I want to say thank you for Professor Buchner and for Professor Nessa Vorobyo. This is my supervisor in the Ukrainian University. I want to say thank you to my supervisor, Dr. Sahara Masrahan, to Sebastian Selter, Robert Kluge, Sabina Miller-Lipani, and all EFF department for all knowledge that I have now. Thank you so much.